Kanish Kumar Patolia, and this is my article summary presentation number 2. Today I'm going to present a really interesting paper from Mayo Clinic published in 2021 that tackles a critical problems in surgical data science using time series machine learning. The paper is titled Early Detection of Post Surgical Complications Using Time Series Electronic Health Records, and it demonstrates how we can predict dangerous bleeding complications after surgery by analyzing patient data over time. So let's dive in. So this is our introduction. So first, let me set the context. So post-operative bleeding or POB is a serious complication that happens in about 12.5% of colorectal surgery patients. Now, why should we care about this? So, well, when bleeding occurs, it can trigger a cascade of other problems like ileus or anastomotic leaks. The mortality rate jumps to 3.4% when POB happens, and hospital stays more than double from 6.5 days to over 13 days. But here is the opportunity. If we could detect this bleeding 24 hours before it becomes critical, we could intervene earlier with less invasive treatments. And we have all this rich temporal data sitting in electronic health records, tracking how patients are doing hour by hour after surgery. So the challenge is that current prediction models are mostly static. They look at a single snapshot in time and ignore how patient health evolves. That's the problem this paper addresses. The challenge? Now you might be thinking, okay, we have time series data, just use a recurrent neural network. But here is the thing, healthcare data is uniquely messy and difficult to work with. First, it's asynchronous. Tests and measurements don't happen on a regular schedule. A patient might get blood drawn at 9 a.m., vitals checked at 11, and then nothing else until 3 p.m. Second, there is massive amounts of missing data. In this dataset, 90% of values are missing at any given time on an average. And traditional approaches try to fix this by filling in missing values with simple imputation methods like using the mean or carrying forward the last observation. But here is the critical insight that makes this paper brilliant. Missingness is actually informative. So let me give you an example. So troponin is a blood test that measures heart damage. Doctors rarely order this test unless they suspect something is wrong. So if a patient doesn't have a troponin test in the record, that's actually a good sign. It likely means they are healthy. Traditional imputation methods destroy this valuable information. So the question becomes, how do we build a model that learns from the missingness instead of trying to eliminate it? So the main objective of this research is clear: develop a recurrent neural network that can predict post-operative bleeding 24 hours before it occurs while explicitly learning from data missingness rather than trying to fix it through imputation. Specifically, they wanted to treat missingness as a feature, not a bug. They wanted to incorporate information about how much time has passed since the last measurement, and they aim to perform traditional static models, outperform. And critically, they wanted a model that could handle real world messy data without extensive pre-processing. That's a tall order, but let's see how they did it. So, methods. Let's talk about their data set and setup. They used data from Mayo Clinic covering 13,399 colorectal surgeries, of which 1,680 cases experienced post-operative bleeding, so about 12.5% positive class rate. They collected two types of data. Static data included demographics, comorbidities, and surgical characteristics, while the time series data included lab results like hemoglobin and vital signs like heart rate, blood pressure, and temperature, and also flow sheet data about documenting ongoing care. Now, to make this computable, they discretized time into 4-hour intervals and tracked patients for 7 days after surgery. That gives you 42 time steps per patient. So the prediction target is, can we predict if bleeding will occur 24 hours from now? This gives clinicians a meaningful window to intervene. Solution. So all right, here is their solution, and this is where it gets really clever. They developed three variants of the gated recurrent unit, or we can say GRU, which is a type of recurrent neural network. First is GRUM, which stands for gated to missingness. They add a binary indicator that tells the model whether each value is actually observed or imputed. They create what's called an input gate that learns to either emphasize or ignore missing values depending on what's more predictive. Second is GRUT, which is time sensitive. This adds information about how long it's been since the actual measurement for each variable. They create a forget gate that modulates how certain the model should be about old data. And third, this is the winner, GRUMT, which combines both approaches. It has both the missingness gate and the time sensitivity gate, and it can be stacked in multiple layers for deeper learning. The key innovation here is that instead of pre processing the data to remove these problems, they are building these characteristics directly into the neural network architecture. The model learns which missing values are informative and which time gaps matter. So, how did it perform? Moving on to the results. So, let's look at the results measured by area under the curve, ROC curve, and we are talking about the mean scores, in which higher score means better model or architecture, we can say. So, the baseline was a gradient boosting machine looking at data 1 day prior, which got 8.58 AUC actually. So, it's pretty good. Standard GRU, as you can see, it got 0.793 as seen here. The GRUM got AUC of 0.842 and so on for GRUT, and GRUMT got 8.66. So the highest was for GRUMT, the area under curve was 0.866. But look at now two key findings we get. First, the missingness gate was actually more impactful than the time gate, which validates their core insight about informative missingness. Second, they improved by 1% over the best baseline, which might sound small but is actually quite meaningful in a clinical prediction task where we are trying to prevent life threatening complications. Moving on, analysis and broader impact. So, let's talk about why this matters beyond just the numbers. Clinically, having a 24-hour early warning system means doctors can do targeted surveillance, intervene with less invasive treatments, and potentially prevent those cascade failures that lead to mortality. So, we are giving clinicians actionable information while there is still time to act. Methodologically, this paper makes an important contribution to machine learning in healthcare. It demonstrates that domain aware architecture design, building models that work with the characteristics of your data rather than against them, can outperform aggressive preprocessing approaches. It challenges the common practice of just imputing everything and hoping for the best. So now let's acknowledge some limitations. This is single institution data from Mayo Clinic, so it needs validation elsewhere. The data set is moderate in size, and crucially, this approach assumes missingness is informative, not random. If your missing data is truly random, this might not help. But overall, the strengths significantly outweigh their limitations. Conclusion and key takeaways. So, the problem was that electronic health record time series data is messy and asynchronous, and traditional approaches lose information. The solution was GRUMT, a recurrent neural network with explicit gates for missingness and time that treats these characteristics as signals rather than noise. And the result was the best performance for predicting postoperative bleeding with an AUC of 8.66. But here is the broader lesson for all of us working in machine learning for healthcare. Sometimes the problems in your data, the messiness, the gaps, the irregularity, actually contains valuable information. Domain aware model design that embraces these characteristics can beat brute force preprocessing that destroys them. When you understand your domain, you can turn data quirks into features rather than fighting against them. And with that, I'll conclude my presentation, and thank you for your time. And sorry for being going over time, but I wanted to explain it in detail. So thank you so much.